Ready to go, Carola?
Yes, ready to go. Sorry.
Yeah, well, thanks a lot for joining us. So we're happy to have Carola Schönlieb today, which will be talking about machine learned regularization for solving inverse problems. Thanks a lot for coming.
Thank you, Knut, and thanks a lot, Katja, also for the invitation. It's really a pleasure to speak in your seminar, especially as someone who is organizing the sister seminar to yours. So it's nice to in some way bring the two also together. Okay, so today I'm going to talk about something that I have been working on for many years actually now, investigating ways how you can regularize inverse problems approaches in a data-driven way while still preserving some of the mathematical analytical guarantees we want to have on the solutions to our inverse problems. So I guess many of you have heard me speaking about this before, so I'll give a recap, and I'll tell you where we are at the moment with this program. Whoops. Okay, so I really, before I go into this, I really need to thank my research group in Cambridge, who are really a great bunch of people. It's a really wonderful group, and without them, nothing would be possible of what I'm presenting to you today. So they are really the reason why I'm speaking to you. So thanks a lot to the group, and thanks also to all the funders from government and industry and private trusts who are supporting us in what we do. Okay, so the main messages of this talk. So I really believe, and so now, as I said, for many years now, that deep learning offers, so when I talk about data-driven, I'm mainly thinking about deep neural networks. And I really think that deep learning offers very interesting opportunities for inverse problems because of their expressivity, because of their capacity to really express information in data sets. And when you think in particular about regularization, which connects this a little bit to the third bullet point here, when you think about what regularization should capture, regularization should really capture prior information I have about the solutions I want to reconstruct for my inverse problem. And so the idea to capture this information from actual, in my case, I work on imaging, from images is very tempting. And I think with deep neural networks, there is a really very good chance now to express this information in a highly accurate fashion. I think the nice thing, or where we as mathematicians come into the game, is that this, in contrast to many of these applications of deep learning, like playing Go or chess or in computer vision, where you have tons of images to your disposal that you can train with, inverse problems can't be solved just like that with deep neural networks. Because of a combination of things, because they are ill-posed usually, and because we usually also don't have this data to our disposal that really would be able to capture the whole solution space. And so we need to, in order to apply deep neural networks, we need to be able to combine them with what we can do very well, or what we have done for many years, which is mathematical and statistical modeling. And in this talk, I'll in particular talk about learning regularizers with neural networks. Okay, I'll skip that. Maybe just for notation, the data that I'm measuring in this talk will be denoted by little y, and the physical quantity, which in my case actually is, in this talk at least, is always an image, is called little u. And although here this capital T looks like as if it could be nonlinear, in general it could be, but in my talk it will be linear, okay? And we can just think of this as a mapping between two Banach spaces. This will be the setting in this talk, okay? And the kind of inverse problems, again, where I'm coming from, the kind of the applications that I'm interested in, they range from various different scenarios. So biomedical imaging, of course, non-destructive testing, remote sensing, but also in a way in computer vision where also lots of inverse problems are, although it's not so natural, I guess, for us to formulate them as such. And again, I'm stressing here. Sorry, these are just a few general slides that I didn't take out, but this is maybe just to stress again that I'm really interested in linear inverse problems that are intrinsically ill-posed, like tomography, where, for instance, with the radon transform, we are looking at compact operators, or in or in scenarios where I really have underdetermined measurements because I'm subsampling and I have noise, and so instabilities are really not good. Okay, and the framework, the mathematical framework where everything starts, in which I want to think about making regularization data driven, is the variational framework, where again, all of you have seen this before, but just again to fix notation, what I'm looking for an approximation to my inverse problem as a minimizer of a functional that I call J of U, which usually consists of these two terms, my data discrepancy term, which, you know, in most cases, let's say, is modeled by a least squares fit between my forward model and the measurements. And that is balanced with a regularization parameter, alpha, against a regularization term that usually captures some prior information I have about the type of solutions I want to reconstruct to my inverse problem. And it's called regularization term because you make your ill-posed problem well-posed by adding regularity to it. Huh? And I have here one example. This is an example that I guess is natural to give for someone working in image processing, because in imaging, very often this L1 type sparsity priors are used, and a very, very common one, a very established one, is the total variation, which in finite dimensions is just a sparsity constraint on the gradient of U. So you're looking for images that where the most important thing for you is to keep the discontinuities, to keep the edges. And this is for images very natural, because quantification, because very often in all the applications that I've shown you, images are reconstructed because you want to quantify something on the basis of them. And so edges are super important for doing this. Okay. So, and the total variation, of course, is just one example. This is just to show you, you know, before thinking about making regularization data driven, of course, you look and see what is out there, what is at your disposal, and there is lots. Yeah, so this is even a subset of things. So there are all kinds of sparsity promoting regularizers. The idea to expand an image in some kind of multi-resolution basis or dictionary, and then assume that it can be sparsely represented there. There are, you know, Banach space norms, Sobolev norms, Besov norms, which have been used as regularizers. And then there are various variants of this total variation idea, where informal convolution regularization would be taking an informal convolution between total variation and some, for instance, in Chambon-Lyon, some higher order total variation, or L2 squared term, indeed. The total generalized variation, which again you can think is related to this informal convolution idea. And in general, higher order TV versions, non-local regularization. So thinking about not just making your regularization dependent on what is going on directly around you, basically, but thinking about making regularization dependent on the global information that is happening in the image. And actually, there is much more now than what I have here in terms of references. These references are all just indicative, but nowadays a lot has happened, for instance, with this PDEs on graphs and things like this, where this non-locality again comes in. Or, you know, going beyond non-linear kind of total variation, for instance, regularization, and even giving your regularization some direction, and so on and so forth. So there are many concepts that people have looked at in terms of how this regularization, how this can be modeled. And there are some really very, very good regularizers out there. But, you know, depending on the situation you are in, depending on the type of solutions you want to reconstruct, maybe also depending on the computational budget that you have, because of course, you know, the more complex you make your regularizer, the more computationally demanding this will be, the model that you get. You need to make a bespoke choice, and that might not be the most optimal one in terms of accuracy, or maybe not the most optimal one in terms of computational efficiency. So just to sum this up, I think all of these type of regularizers, what they have in common is that they really take advantage of the fact that you know, solutions to such variational problems or associated PDEs can be characterized by just a few relevant features. And if you assume that images behave somehow similar, that they can also well be approximated by this, then this works. And this works very well. I mean, just look at an example of what kind of difference this makes to problems like here, computed tomography. This is a simulated example where we have a sparse angular CT measurement that we have simulated, and this is the filtered back projection of this measurement. This is here on the left is the ground truth. We can think of the filtered back projection as an unregularized reconstruction, let's say. And then we look at the variational reconstruction with the total variation as a regularizer, and we get this. Yeah? So if I go back and forth, then, you know, maybe for a trained eye, you can maybe distinguish what is actually structure and what is not, but there is lots of additional kind of diversion in this picture with not just the total variation, but with a proper regularization. You kind of boil down more, you kind of focus more on what is actually important. And again, this is not the only thing. So somehow with all of this, the idea came, can you use data to help come up with new regularizers? Okay, and this is what I want to talk about. And again, this slide is mainly when I'm talking about this in front of you know, more machine learning oriented people. Let's say I'm really interested in problems. Maybe starting here, I'm really interested in problems which cannot be killed basically with huge amounts of data. So we do, my kind of approach is that I'm starting with a well-posed mathematical framework, like a variational model. And I use the data-driven component where in a way that, well, where I think I need it, and then also trying to make that in a way such that we can still have some guarantees at least preserved. Yeah, and please also interrupt me. I mean, at the moment it's just general blah blah still, but please do interrupt me if you have a question. Now we are starting with the actual thing. So, and maybe another thing to say, because I was not planning to give an overview of all kinds of deep learning approaches that have been proposed in the last couple of years for solving inverse problems. But let's say a majority of them is really using deep neural networks to really solve the inverse problem, to reconstruct. I really want to use the deep neural network to learn a regularizer, okay, to learn an image prior, and then I go back to my variational model with this regularizer and I solve it. I of course have to make it in a way such that the regularizer still gives me a variational model that has some properties, but we'll get there. Okay, so this is joint work with a couple of people. Everything actually has started with Sebastian Lund, who has just submitted his PhD thesis and will hopefully defend next month. So with Sebastian and with Ozan Öktem, we have written this first paper that got published in NeurIPS in 2018, which is called Adversarial Regularizers and Inverse Problems. And I'm going to start with this and I explain this to you. And then we have thought a little bit more about this and also got some more people on board. So Søren Dittmer is a former PhD student of Peter Maas in Bremen, and he's now working with me as a postdoc in Cambridge. Shubho Mukherjee is actually, he just said this yesterday. He did his PhD at IIT in Bombay, maybe. I've forgotten now, in India. And then was a postdoc with Ozan and now recently joined me. So you see this kind of roundabout thing here, but he recently joined me and now we are working together, actually still together with Ozan on a cancer imaging project. And then Zach Shumyalov, who is actually an undergraduate student in mathematics with us. And he has been working with us now for the second summer on some ideas around using data-driven ways to solve inverse problems. And he's extremely good. He's just has started his third year. And when we worked on this, what is now the update kind of that I'm giving you today, which is the second paper where we are basically making this adversarial regularizer convex or strongly convex. This is something he did after 1 year of 1 year of math undergraduate. So it's he's really good. Okay, so let's get into this. So learning variational regularizers. The idea, again, just to set the scene. So we have, this is my variational problem. Now I'm really in the linear setting. My forward operator is linear and bounded between two Banach spaces. And what I want to do is I want to stick to this, but I want to learn the regularizer. And this has several advantages, in my opinion. You have you are really learning and you are learning a prior, let's say, for the problem you want to solve. You are still, and I'll show this, you'll still get some stability and convergence guarantees for the solutions to this problem. You can play around with the regularization parameter and actually I'll also briefly show, if there is time, that the regularizer is actually quite stable in how you train it with respect to different noise levels. So you can still tune this with your alpha here. You have the forward model still in the model, okay, and very explicitly. And you can play around, of course, with the data discrepancy term and not just an L2 squared fit, but you can use different things depending on your noise statistics. So when you go about making regularizers data-driven, of course, you start thinking of what has been done already in this context. Even, this kind of idea is not new. This has been around for many years, and before neural networks arose. And here are just a few examples, and all my references are super incomplete, but should just give you some first, I guess, idea where to look for more information. So, oops. So one big kind of family of learned regularizers comes from this idea of sparse coding and dictionary learning. And this, when so Simon Erich, Peter Maas, Osa Nögtem, and myself, we have written now already 2 years ago, we have written an Acta Numerica paper on this data-driven approaches to inverse problems. And then we really looked through all this literature. And the interesting thing was that this kind of sparse coding dictionary learning idea really was mainly used in signal processing. So it really didn't really make it so much into inverse problems. And if any one of you has an opinion on that, would be interesting to hear. I don't know exactly why, but the idea here is that you again want to reconstruct the solution to your inverse problem by using a sparsity regularization, an L1 type of regularization. And you do this by expanding your solution as a linear combination of what is here called dictionary elements. And then you want the coefficient vector to be sparse. Okay, so this is basically this we had already kind of before when I talked about multi-resolution analysis and this kind of things. But now with dictionary learning, the idea is that you do not just solve the problem here for gamma, but you also solve it for phi. Yeah? So you also make the dictionary elements themselves unknowns. Yeah? Okay, so this is one way to say what is my regularizer, in which kind of representation should my image be sparse. Another thing that actually got, again, kind of highlighted in last year's SIAM imaging conference is this idea of plug and play or regularization by denoising. I don't know if I don't know who of you was at the SIAM imaging, but the 2 prizes that were awarded by the SIAM imaging activity group, one was the best paper award, and one was the early career award, were both awarded to this type of thing. So one was for plug and play was awarded to Charlie Booman, and the other one was awarded to Romano for the red paper. So here the idea basically is that there is a way how you can set up your regularization in your variational approach such that what it defines is a denoiser. So you could, so the idea here is you have such a large collection of image denoisers that people have developed, and some of them work really, really well. Can we make use of this pool of really super performing denoisers and use them to regularize inverse problems? And so so I guess talking to an inverse problems community, probably many alarm bells that are ringing when one talks about it like this. And indeed, the theory for these type of approaches is not very well established. In particular, so you can imagine the denoiser needs to fulfill various constraints that in the end make it quite restrictive of what kind of denoisers you can use in order for that to be actually a valid regularization. But yeah, but this is still interesting, and I encourage you to have a look if this sounds intriguing. The other idea that actually I also started with thinking about data-driven regularization is this idea of bi-level optimization or PD constraint optimization. So to basically say, okay, I have my variational problem and I have my regularizer, and I have some good candidate regularizers, or I have a way how I can parameterize my different possible regularizers. Okay, so this could even be in a way this in this context here. Yeah, so you have a way you parameterize your regularization, and then you are optimizing over these parameters that make up your regularization by minimizing an additional evaluation criterion, yeah, which maybe again, when you think about machine learning, maybe it's called the loss function or something like this, yeah, and which in many cases, for when people are optimizing for these parameters here in the variational problem, would just be that you compare the solution to your variational problem, which now is dependent on lambda. You compare that with some ground truth solution, and so so usually this would again be in a kind of supervised learning fashion, where you have a training set of different images and corresponding measurements, and then you learn this parameterization by minimizing the least squares fit of your solution u lambda to the ground truth solution, and then you take the expectation of this over your whole training set. So this would be bi-level optimization. It's called bi-level because you have an optimization problem on 2 levels, and I said PDE constrained optimization because the mathematical analysis for this actually very often boils down to looking at the optimality conditions for this variational problem, which are then, when you're thinking about taking a gradient based regularizers, would be some type of PDE that you're looking at. So you're looking at a minimization problem with a PDE constraint. Okay, so so that's it. And then there are deep neural networks as regularizers. And again, again, in the context of using deep learning for inverse problems, there is now lots of things that are happening that people are looking at. Using deep neural networks as regularizers, there is also a bit, but maybe there is not as much. And I mean, one motivation, maybe now I said all the time that this is great if we stick to a variational problem. One motivation maybe why is not too many people are looking at this in the context of a variational approach is that you still need to solve a variational problem in the end, which in a way is another motivation for some people to use neural networks to solve inverse problems, is that once they are trained, they are just a concatenation of matrix vector multiplications, basically. So that is all explicit. So you don't need to solve another optimization problem once the network is trained, which of course now I still need to do. So yeah, okay. Okay, so now let me tell you how we are doing this. So I now want to tell you how we are learning the regularizer. Okay, I told you before that our regularizer is called adversarial, and it's called adversarial for a reason. Namely, this is how we are thinking about optimizing this regularizer. Okay, so the idea is maybe let's start here with a formalization. So I wanted, or sorry, let's start here. What I want is I want to tell the regularizer that it should favor solution structures that I want to see in my solutions to the inverse problem. And on the other hand, I want to tell the regularizer that it should suppress, noise or characteristic artifacts of my inverse problem. And very roughly speaking, and I'll show this in a second, how we do this is that we are optimizing the regularizer to be large for these noise and artifacts, and to be small for the kind of structures that I want to see in the solution. And the kind of structures I want to see in the solution will be examples of ground truth images that would be would have a good resemblance with the kind of solutions to the inverse problem at hand. Okay. And so for this, I first need to the thing that I need to prepare my regularization to train it are these two different sets of images. Okay, I need images that are noise images, and I need images that are ground truth images. So what I do is I'll define two distributions that will then, in the finite dimensional case, will be made up of training sets of these ground truth images. And then I want now to also, so this is my distribution PR. This will be the distribution of ground truth images. And then I want now the images that show all this noise and artifacts, and I'm creating them through first of all looking at the distribution, at the data distribution, so the distribution of measurements, and then applying to all the samples in the distribution of measurements, I'm applying the pseudo inverse to those solutions, and I'm creating this distribution PN. Okay, so this is now another thing that we, at least how we did it, we only solved inverse problems where we could compute the pseudo inverse. Yeah. Again, why did we chose the pseudo inverse? Because the pseudo inverse, like for instance with computed tomography, would be the filtered back projection, shows you not just the noise that you have in the data, but it when you look at the corresponding images, but it also it typically shows you the intrinsic artifacts that the forward operator encodes. So the intrinsic artifacts that come from the ill-posedness of your problem, like in filtered back projection, you see these streak artifacts and things like that. Okay, so this is why we chose it. But if you have another way, another inverse problem where you don't have the pseudo inverse, then you would need to think about some other way how you create this distribution PN. Okay, and so now our aim is to train the regularization functional such that if you feed it with images from this distribution PR, then it should be small. And if you feed it with images from the distribution PN, then it should be large. Okay, so this is just here given again in terms of pictures, basically. So this is CT again. I'm only actually showing you CT here in this talk. We also did this for deblurring, and we also Sebastian actually did this in his PhD thesis also for MRI. But yeah, it is it all shows very similar kind of results. So this is CT. So this is your a ground truth image. This is a sample from our distribution PR. Then this is my simulated. This is simulated at the moment, but of course, if you have real measurements, that's even better. So this is my sinogram, in my measurement space. And then from this, I'm creating my images, my samples from the distribution PN. Okay. And maybe one thing to highlight here is that that you will see in a moment, because my evaluation criterion is, on the one hand, the regularizer should be small for these guys and should be large for these guys, which does not necessarily mean, if I say it like this, and you will see it on the next slide, does not necessarily mean that for evaluating or for optimizing the regularizer, these two need to be paired. Huh? So you could have measurements and no ground truth if you have a way to create or to access ground truth looking images, or at least images which you think should influence how the regularizer is optimized. So how do we do this now? What is the criterion? How do we formulate the criterion for the regularizer? We do this via the one Wasserstein distance between the distributions PN and PR. And how is this linked to the regularizer? Well, it's linked to the regularizer by looking at the Kantorovich dual formulation of the one Wasserstein distance, which if you are not into optimal transport, then actually this is the most important line here, which is we are looking for a regularizer as the one Lipschitz function that maximizes this difference here, where you are maximizing the regularizer when you're feeding it with samples of Pn, then it should be large, okay? And it should be small, so there's a minus in front, if you're feeding it with samples from the distribution PR, which is your ground truth, your distribution of ground truth images, okay? And then the optimal one is basically should be my regularizer then. Now, neural networks come in, and they come in a couple of slides later. This is why I'm briefly saying it now. Neural networks come in order to make this basically accessible, is to have a parameterization for these one Lipschitz functions. And the parameterization for these one Lipschitz functions will be then that I represent them as a neural network. Okay, so this will be, I'll explain this then in a moment. So first of all, is such a criterion for looking for a regularizer, does this make sense? And here are some kind of hints towards that this might make sense. So if you think about it, what you want to do once this regularizer is trained, you want to plug it back into your variational model, and then you minimize this variational model, right? So in a way, what I'm doing here on this slide is I'm looking at if I'm going in the, if I'm minimizing the regularizer that I get from this, and I do a steepest descent for minimizing this regularizer, does this take me in a direction I want to go? Okay. Okay, well, so this means if I'm starting with a sample from a distribution Pn, which is the distribution of noise artifact images, and I take this and I take a negative gradient step, a negative gradient step if I take a step in the direction of the negative gradient of the regularizer, then I get new images, I get new samples that I call G eta, and I get a new distribution that I call P eta, okay? And somehow what I'm hoping is that these G eta of you are better than the ones I've started with. And they are better, at least in the following sense, namely that if you do this, then this step actually takes you closer to the distribution. So this P eta is now the distribution of the images that you get when you do this step. And this actually you can show takes you closer in terms of the Wasserstein distance to your distribution of ground truth images. Yeah, so this, you're going in some good direction, let's say, distribution wise. Another thing that you can show, and now the assumptions are getting a bit stricter. So this is maybe one thing that at the moment, and you know, I'm really working hard on, and many people are working hard on trying to change this. One problem is, of course, that the moment you make this regularizer neural network, or you optimize it in that fashion, the interpretability is very small at the moment, at least. So these are just some attempts that in some scenarios to say a little bit more. And the scenarios are now the following. So the first one is if I assume that my distribution of ground truth images is in some ways well behaved, which means that I assume that PR is supported on a weakly compact set that I call M, okay? And so this is, okay, this is maybe not, is an okayish assumption. And then the other assumption is tougher because it's a kind of, you can think of a kind of small noise assumption. And the assumption is that I can recover the distribution of ground truth images by projecting them, by projecting the distribution of noisy images onto this manifold on which the distribution of PR is compactly supported. So you could think of this as a kind of low noise assumption. Yeah? So if we kind of accept this, that we are in this subset of problems we want to solve, then you get some additional interpretation of what this regularizer looks like, or what it is. Namely, what you get is that the distance function to the data manifold is actually a maximizer to the is a maximizer to this Wasserstein loss, which means is a candidate regularizer for your learned regularizer. Okay. Okay, so let's see this now a little bit in action. So now what's the idea? So the idea now is practically what we do is we approximate the one Lipschitz functions with a neural network. So and now I'm kind of renaming them. So instead of F, I'm naming them psi theta. So psi theta are now neural networks that map images of size. So this is all now discrete, okay, this explanation here. Images of size n cross m to a real value, right? That tells that is the value of the regularizer of this image. And then I'm training. When I say training this regularizer, I mean optimizing over the parameters that make up this neural network by minimizing now this approximate Wasserstein loss, let's say, which is motivated by work that people have done in generative adversarial networks, where they have used these kind of Wasserstein distances as discriminators, as loss functions, where this is the same as before, okay, as we had before, now just that we have neural networks here. And of course, in reality, these will be now empirical distributions. And then I'm relaxing my one Lipschitz condition by this additional penalty term here. Yeah, where I'm basically fitting, I'm imposing the one Lipschitzness by fitting the gray, by encouraging the gradient of phi to be less or equal to 1. Okay. Okay, so and then the idea is, the whole algorithm is that I train the regularizer in this fashion with this distributions PR and PN. And once I've trained it, I plug it back into my inverse problem, into my variational problem, and I solve it. Okay, and then I solve it. I could do gradient descent or whatever I can do. Okay. Now, in this context, so the one thing to say is the only thing I know, at least, you know, even I don't know this numerically in finite dimensions, I know this asymptotically. My regularizer is one Lipschitz. This is the only thing I know. I don't even know whether it's bounded from below, at least from the construction that I've just shown you. So in this setting, you can prove that a minimizer exists. You can prove that you get super weak stability. I mean, super weak, you get weak stability, okay, depending on the topology that you have in your Banach space. But you actually can come up with counterexamples that you can't get stability in norm or something like that. Yeah? Now, and this is now the update, and I think this is quite nice, and I think we need to go further in this direction to actually put more constraint onto this regularizer, and convexity is a first try. Okay, so one nice thing is that there are people who have looked into convexifying neural networks. Yeah? So you can parameterize neural networks in a way such that they are convex. And now what we have done is we have now optimized over such networks that are convex, and we have added a little L squared term such that my regularizer actually is strongly convex. Okay, and if I'm in this setting, then I can, you know, then I have existence, I have uniqueness, I have strong convexity, I have stability, I have convergence of the regularization, and also the algorithm that I use to solve in the end my variational problem is of course convergent. Yeah, this is all strongly convex. So this is nice, and this is just how you can create these convex neural networks, which I'm happy to tell you later if there is time. We can go back to that, but I'm quite keen to show you some examples of what you get with this. So so this is again simulated, and and this is really mainly the work of Schubo and Zek, who have been looking at this Mayo Clinic OpenCT dataset, and have done two types of experiments with that. Okay, so one is Sparse-view, where they have taken this and simulated Sparse-view data. So here you have some details, but I'll show you in a moment. So this basically means that you have measurements kind of everywhere, but they're very sparsely distributed. So not a lot of angles. And then here, this is something that Zek did mainly, is limited view. So here you really have a whole wedge of angles missing. Okay, so 60 degrees of missing angles. And the results I'm showing you are, okay, so filtered back projection, total variation regularization, then the adversarial, the original adversarial regularizer, which without convexity, the adversarial convex regularizer reconstructions, and then the last one is an approach that maybe some of you have seen, which is this another deep learning approach, which is not going back to a variational problem. Okay, it's called learned unrolling or learned primal dual scheme. And here I'm just here in parentheses, this is supervised in the sense that here you're really comparing. You really need pairs of images and data in order to train this. Okay, so let's see how this works. So this is now just one example, yeah? This is Sparse-view CT. So the first example where you have a sparse number of angles. This is the ground truth I'm always showing here on the left, and then on the right, I show you the reconstruction, okay? And what you see here on the bottom is basically, this is the PSNR of the reconstruction, and this is the so-called structural similarity index measure, SSIM. Yeah? So these are, the larger those are, the better. So this is filtered back projection. So this looks like this. This is the total variation. So, I mean, I've worked now on variational regularization for many years, but just to say that is still quite impressive in a way, right? I mean, the image doesn't look that great in terms of looking close to the ground truth, but you have, when you look at the quality measure, yeah, so the distance is a kind of distance function to the ground truth, then you really make, in terms of dB, you make a jump from 21.6 to 29.2. Yeah? And so this is, I think, is quite remarkable still. Well, this is what you get with this deep learning based reconstruction, which is our kind of comparison here in terms of deep learning approaches, which is not a variational one. This learned primal dual. So you get, here you have another jump, you have 29.2 and you jump to 33.6. And you maybe also see that you really recover, you can really recover some, yeah, some details that you would not see so well with the total variation. This is what you get with the adversarial regularizer. So you lose in terms of accuracy, definitely. But maybe you gain a little bit in smoothness. And this is the adversarial convex regularizer. So actually you lose again a bit, yeah. And in a way, it's not that, it's a little bit better than TV. It's like maybe 1 dB better than TV. But now you have something that is also closer to TV in terms of mathematical guarantees. Yeah? Now, I think what is actually impressive is the limited angle CT. So this is a filtered back projection, okay, this result. This is what you get with TV. So this is already, again, quite a jump. This is what you get with the learned primal dual, so this deep learning based reconstruction. This is what you get with the adversarial regularizer. So here you definitely see the theory already kind of warning you that things can go terribly wrong if your inverse problem is very ill-posed. Yeah? And this is what you get with the convex regularizer. So then again, you see that here somehow the convexity of this regularizer kind of saves you from doing too much harm. And in comparison to TV, actually, you make another jump. So this is 25.7. And I mean, this is now anecdotal because I'm showing you only examples here, but you will see if you look at the paper. Sorry, I didn't put a table in here, that this is really kind of what the story in general looks like. You are making another jump here to 27.97. So that's quite nice. So open problems. So I'll finish with this now. And there are lots of open problems, of course. Yeah. So, and these are just some open problems, I guess, that we came up with and that we started thinking about. But yeah, so and this in particular, I guess, also in this variational context still. Yeah. So in this learning a regularizer. So so one of the questions is, of course, if you train a regularizer on a data set, how determined is this? I mean, how specialized is this for the training set, and how much worse does it get if you apply it to another one? And at the moment, we only have empirical investigations that would answer a little bit this question, and this is in the PhD thesis of Sebastian Lunz. I'm very interested in actually really studying this, and actually the very good news, so I'm telling this now to everyone because I was so happy last week, I got a 5-year research fellowship starting a bit later in a couple of months, which is really kind of where I'm very determined to look in developing this more, and in particular looking into the theory. But sorry, and in the PhD thesis of Sebastian Lunz, what he has been doing is a few experiments along these lines. So he did cross dataset experiments. So here, for instance, this is his original adversarial regularizer trained. So trained on knees. So this is here on the left. This is the images that it's trained on, and this is the images that he has applied it to. So this is again for CT is a bit of a strange color coding. Sorry, but this maybe is a bit easier to see some of the structures. So this has been trained on just these images, and here you see a reconstruction with the adversarial regularizer trained on these but applied to these. And again, for more, this is again just a teaser for this. And here this is the other way around. Yeah, so this is now trained on the lungs, but then applied to the knee. What else do we have? Yeah, cross noise experiments. So this is also interesting. So here the adversarial regularizer is trained on high noise. Okay, on high noise and the distribution PN. And here you see how it looks if you apply it to low noise CT measurements. And here again on the right, you see how it looks when you apply it to high noise measurements. I appreciate that for some of you this is super small. Actually, for me, it's also small if I look at my screen. But I'm very happy to send you the Sebastian's PhD thesis, which I think is not yet published because it's still with the examiners, but I'm very happy to send it to you. Here you see the other way around, and this is where it doesn't work so well. If you train it on low noise and then apply it on high noise, I mean, this is maybe also natural that this wouldn't work so well. Okay, so these are just a few experiments. I think I don't have more now, but then a few other things. So stronger constraints would be nice. Yeah. So what about, for instance, enforcing source conditions or things like this onto your trained regularizer, which, you know, with convexity now kind of makes sense. Now that we can train a regularizer, I've said before, you know, why the total variation has been so successful for inverse problems in imaging is because very often we are not just reconstructing an image because we want to look, because it should look nice. So this is not our optimality criterion that it should look nice, but that it should be quantifiable for another image processing task that comes afterwards. And so this training the regularizer now, being able to train a regularizer, we can train it with different criteria, right? And now I've presented you one criterion of how you can train it, but you could make that more task adapted. Tell the regularizer that you want the best image, or the image that is best for doing a segmentation afterwards, for instance, or something like that. The bottleneck of all of this is, of course, if you have very large data, 3D, 4D data, where you're training regularizers for, then the bottleneck is already in the training, that you run out of memory when you're training for such large networks. And so something that we have been looking into is what people are calling invertible networks, which are memory saving. And there are lots of more questions. Uncertainty quantification. With the convex regularizer, again, this looks like it would fit really well in Marcelo Pereira's proximal MCMC framework. And then the interpretability. In a way, you know, the dream would be in a way that, what about you tell me what properties you want from your regularizer, and I give you the right training set to train the regularizer in that way. Yeah, that would also be nice. So, all right, so takeaway messages. So I still think, although you need to be super careful, yeah, this is also something I think is that deep learning has a lot of promise for solving inverse problems, if you combine it with the tools that we already have, in a way that still gives you, that still preserves some of the solution guarantees. And there are many open questions, and I've just shown you some. Yeah, and I thank you very much for your attention. Thank you.
Great. Thanks a lot for a great talk, Carola.
Thank you.
So if there are questions, please unmute yourself and ask questions.
So I have a question, Carola. When you were showing, you said the theory shows you how it can go terribly wrong if you do the adversarial, which isn't convex. Can you tell us what goes terribly wrong there?
The problem is that the adversarial, so the adversarial regularizer is trained without any constraints. Yeah? So the only thing that you have approximately is some kind of regularity through this one Lipschitz constraint. But this also means that it's not bounded from below. So your solutions could shoot off to minus infinity in a way. This is also what actually breaks the strong stability. So I think you just see something that comes from that. It's not really it's not really capturing it's not it's just instabilities of the regularizer that are coming through. Yeah.
So I was wondering, Carola, so you talked about perhaps incorporating prior statistics on the noise. So for the examples, you talked about high and low noise. So how did you sort of use additive Gaussian noise, or do you sort of try to adapt the noise to the problem at hand when you generate the data, PN?
So in general, I think the message is the more your training set resembles the actual scenario you want to you want to solve, the actual scenario of the inverse problem you want to solve, the better it will be. So then it would be good to actually have really the right noise in your training set. What I've shown you is that it's, the example I've shown you was just with Gaussian noise, and we just, what Sebastian did was that he used two different standard deviations for the Gaussian noise in creating the training data set. And what his experiments just show is that it's relatively stable with respect to a change in the noise, in the noise in the strength, let's say, of the noise in the standard deviation. But more stable if you train on stronger noise than if you train on weaker noise and then want to solve the problem on measurements with a larger standard deviation. Yeah. So I have actually not, so at some point also he was running out of time with his PhD thesis, but I mean, that would be interesting to see how, you know, if you go from Poisson noise to Gaussian noise or something like this, how that would work. I mean, in a way, you hope that this is captured by your data discrepancy term, but then of course your distribution PN will also very much feature that. Yeah. Mm-hmm. So your regularizer should know what type of artifacts it should counter in a way. Yeah.
Good.
Should I unshare my slides?
Yeah.
Maybe then we can see each other as well.
Good. So any more questions for Carola? So I was wondering also when you learn a regularizer, do you sort of adapt also the structure of the neural net, for instance, or do you sort of choose this a priori?
Yeah, so we have not really played around this too much. We are just choosing kind of off-the-shelf convolutional neural networks. Yeah. So that's it. But yeah, that would be definitely something to explore. I'm not so terribly interested in this myself, but I think that could be interesting. That I mean that in general could be interesting. Yes.
So what about the case if you have sort of some nonlinearity with nonlinear problems?
Yeah. Yeah, so again, I think that there is a whole you know, new, there is definitely a large class of problems that we haven't been looking at. I wouldn't also be the right person to look at this. I've basically, you know, almost conclusively been working on linear inverse problems in my career, but so I also wouldn't have the right expertise actually to look into this. I think it would be very interesting if people would be looking into this. You would need to have a way to so I think at least our way how to train the regularizer kind of always depends a lot on that you are able to create this distribution of PN, right? This PN distribution, this distribution of noise, noisy reconstructions. So you would need to have a good way to solve your inverse problem naively in a way that would show, that would somehow resemble the, I mean, you could solve if you can solve a least squares fit to your nonlinear operator, I think that could already
maybe be something like this, maybe with a minimal norm constraint. Or, I mean, if you could solve some, I mean, that's kind of the pseudo inverse, right? But if you could, yeah, if you would have some proxy for doing this, then you can do it. The problems, then you can do it. Yeah.
Great. Okay, well, if there are no more questions, let's thank Carola again for a very interesting talk, very nice, learned a lot. So
thank you. Thanks a lot for inviting me. Thank you very much.